it's a topic that's been sort of near and dear to my heart, and actually a topic that's been bugging me and the community for a very long time. Is the topic of like sort of data sharing and data sets in the systems and networking community. So the lead students here were Yucheng and Zinan, who are PhD students, and Minhao, who's a master's student here. And this is joint work with my colleague Julia Fanti, who's a machine learning and privacy researcher here at CMU. Okay. Now, the context for this work really comes from the fact that I think you all probably seen this, that the entire world, including networking and systems, is very much moving towards a very data-driven approach, right? So if you are collecting network data or systems data, there's a lot of applications that are in production, in operations, that are using this data-driven approach by collecting a lot of traces. So for example, you can use a network trace to understand the structural properties of your traffic and use that to determine how to best manage resources, assign VMs, assign network resources, and so on. People are using these sort of network traces, for example, for predictive modeling. So I think for example, in networking, you want to forecast, you want to predict traffic. In other things like cyber physical systems, people are also using these traces to do proactive or predictive maintenance, for example. Data-driven analysis is also very commonly used to evaluate and check different kinds of like algorithms that you want to develop, right? Say you've come up with a very cool machine learning algorithm or a very cool resource management technique. You want to evaluate how well it will operate in the real world. And to do that, you need realistic traces. And finally, there's a lot of like data-driven approaches that are used in security and resilience as well for detecting attacks, anomalies, and alerting when such things happen. So the bottom line here is that sort of the world has moved on from sort of handcrafted custom approaches to a very data-driven approach where network traces and header traces are used to drive a lot of key operations and sort of research activities. But here's the catch. The catch here is if you're in academia and there is this sort of data-driven research being done in industry and by other academics, we currently have a reproducibility crisis in academia. So because the data sets that are being used to drive this research, inform this research, develop these machine learning models is not public, that research is fundamentally not reproducible. I can't validate other people's models. I can't validate their algorithms or build on or extend them because the data sets are private. Okay. Now, 20 years ago, there used to be a crisis in academia of reproducibility where the code used to be proprietary. Now, we've actually done a very good job over the last several years where there is a culture of open source, where I put out my code, you put out your code, and artifacts are actually evaluatable and actually artifacts are reproducible. We've done a fantastic job with source code. But now the problem has shifted where data has become sort of the primary stumbling block, the primary bottleneck for reproducibility. Okay. Now, there is also a collaboration problem or a collaboration crisis. So imagine you are a researcher at IISc and you want to work with different companies. Now, those companies have like interesting data sets to validate and test out your algorithms, but that collaborative opportunity is currently untapped or you cannot even exploit it. And it's not just a pain point for you. The companies also want to tap into your mind share and tap into your cool techniques, but they're unable to collaborate today. So unless you go physically become an employee or an intern, it's very tough to collaborate between companies and academia. This is also a problem for collaboration within companies or across companies, right? So some companies trying to evaluate different kind of vendors or are trying to collaborate between two different customers. That collaborative opportunity is also going untapped today because the data is being locked away due to proprietary reasons or compliance reasons. Now, you might think this is just a problem for academia, but it turns out that this is also a problem in industry, right? There's a number of like networking, security, and systems companies that are developing analytics products and ML-based services, but even they have this sort of problem where the data they're collecting is either not available or locked away, or due to compliance reasons is not available to their test and machine learning teams. So as a consequence, those products are also suffering. So for example, one vendor told us that they are unable to reproduce what their customers are seeing in the production network because they don't have access to those logs. So for example, when a customer sees an attack or an anomaly, their test teams are tasked with reproducing that workload or reproducing that incident in the lab, but they're unable to do it because they cannot access the customer workload. Similarly, the data science teams today want long-term data to test and build robust models, but because the data is not available, they're actually not able to build robust models or test out their models at scale. So this is not just an academic crisis. This is also a realistic crisis in industry as well. And it's getting worse in the sense that as more privacy regulations, some of you may have heard of like things like GDPR. Again, many countries and many states are actually coming up with new kinds of like privacy and data regulations. As these regulations go up, this non-availability of data only becomes worse in the long term. Okay. So our vision is really to sort of break away from this this problem, right? How do we enable data sharing between sort of collaborating partners, where a data holder, say in this case, we are focusing on specifically on network traces, so the kind of like packet and flow level traces that ISPs and telcos and other kinds of like sensor networking deployments are collecting. So we want to be able to build this platform called NetShare, where you can specify what kind of fidelity properties are of interest to you, right? What statistical properties, what kind of machine learning anomaly detection task you want to run, as well as privacy properties, saying, okay, these attributes are private. I don't want these to be revealed. These IP addresses need to be masked. And given those fidelity and privacy specifications, we want to be able to generate high fidelity synthetic traces that are privacy preserving, right? So again, the key here is privacy and the fidelity. And once I have these synthetic traces, I can use them for any kind of downstream task that you have. Now, the nice thing about these synthetic traces, in contrast to other approaches like say federated learning or computing over encrypted data or homomorphic encryption and so on, is that it's actually a much lower friction and a backwards compatible way of doing your existing workflow, right? I don't need to change what machine learning toolkits or my Python code. I just take the trace in the same format that it came in originally. I can treat it as if it was the original data. And the nice thing now is that because I have more data, I have synthetic data, I have realistic data, it helps my workflows be better, faster, and more robust. Okay. Now, the question is, how do we actually build this entity, right? How do we build this NetShare module, given that this has actually been an open challenge for the last several years? In fact, I've been in the networking community, in the research community for the last, ever since grad school for 20 years. And this has been a fundamental pain point for us, where the lack of access to data has stymied these kinds of collaborative opportunities. Yes, Parimal, you have a question. Please.
So what is the input to NetShare? The IP header traces, PCAP and network, is it coming from industry or how is this?
Yeah, great question. So in our research, we have used public data sets to validate our approach. But in the future, what we envision is that any data holder, right? Say whatever, Reliance Telecom in India has a bunch of traces and they want to collaborate with IISc, they can use NetShare to generate traces and share it with you, right? Basically, somebody who's collecting the data, right? Or it could even be like IISc's own university network is collecting this data all the time, but they're unable to share it with you or their researchers and so on. So any data holder who's collecting will run NetShare and then share that synthetic data with other people who are interested in building on it.
Right. So if my understanding is correct, your input is still going to be realistic traffic based on which you're going to build some kind of model and then output synthetic data, which may not be exactly what is input, but you're still going to build a model from real data, right?
Exactly. The input is still real data that has been collected in a production environment in an operational setting. Then we build what are called generative models, and I'll get to that, from which we generate the synthetic traces. Yeah.
Understood. Exactly. So my trouble is still the following. Suppose you don't have this left part of this thing, right? I mean, then I mean, like, so if in absence of this realistic traffic, it's difficult to come up with something to justify, right? This model which you don't know how to
absolutely. Again, yeah, this is again, people have the data, right? So that is actually not, that is a non-problem. People have data, they're just unable to share it. Everybody is collecting a ton of
but
data.
But they still have to be sort of convinced that, right? So I agree with your proposal, answer, but they still have to be convinced to use NetShare, and they think that what I'm going to learn from the synthetic data is nothing what they are trying to protect, right?
Correct. Yeah. Again, this is the first step, right? So again, there's
right.
going to be like all sorts of like convincing and incentives and so on. Now people have incentives to share data, right? Both within companies, within academia, with across, even within say different organizations of the same company, they want such a tool. They don't have it, right? Given the lack of such a capability, they are not doing this. It's a 0-1 right now, but at least now we are changing the game, starting a conversation of saying, hey, what if we gave you this sort of a capability, then at least that changes the game from sort of a binary, right? Today, it's all or nothing. Either you get all the data or you get nothing, right? So at least now we can say, hey, look, okay, maybe there is a more pragmatic middle ground where you can do your workflow with synthetic data and then maybe go back and ask for more data and so on. Yeah. Today it's binary, right? So either you basically have legal contracts that give you all data or no data, right? But the capability now, we are building the capability to enable new kinds of collaborative opportunities that were previously untapped. Yeah, but you're right. The left-hand side has to be realistic data that is coming from somewhere. Okay, cool. Any other questions? All right. Yeah, thanks for the question. Yeah, keep them coming. So this is great. The more interactive, the better. Okay. So before I jump into like how we did it, right? So again, the goal of this talk is to sort of say, okay, evangelize NetShare and say, okay, look, you should all be using NetShare. But then getting that to work is actually non-trivial. So let me tell you a little bit about how we got there, what are the core techniques that we're using, and so on. Now, and in fact, this problem, as I said, is not a new problem, right? Ever since people have been doing research, people have been trying to get data and traces to do that. And in fact, as Parimal mentioned, historically, we didn't have realistic data. So what people did was writing simulations and their own statistical models to generate this kind of data sets. Okay. So for example, you could write a simulation in NS3 or any other kind of simulation tool, or you model different kind of like statistical properties, like, okay, it's a Poisson arrival, it's a Markovian process, whatever it is that you want to do, and you can generate your own data, right? So that is what people were doing in the absence of realistic data sets and so on. The problem with this approach is actually it requires a significant amount of like domain expertise and human effort to create these kind of realistic models. And at the end of the day, it's actually very hard to actually reproduce the patterns we see in the real world. Right? The real world is extremely complex. It's very hard for a human-driven model with these few statistical parameters to accurately capture the complexity and the high dimensionality that we see in the real world. Now, on the other hand, there are these recent advances in machine learning, in particular, generative models, including some of the work that we have done, that are actually promising, and which is, we are building on that promise, but they're not quite effective directly off-the-shelf techniques that work for network traces, and that's the problem we're trying to solve here. Okay. Now, in particular, we are approaching this problem from the perspective of what are called generative adversarial networks, or GANs. Now, GANs were this sort of really cool breakthrough result that came about in 2014. And at a high level, you've probably heard about things like deep fakes, right? From a given data set of images, or like celebrity images, or like cars, or whatever it is, you're able to learn a structural model of what the data set looks like, what the data looks like, and then produce new samples that were not seen in the data set. Okay. So at a very high level, so I give it a corpus of faces, and then say, for example, learn a generative model or a GAN, and then it produces a new face that we have never seen before. In fact, the faces on the right, and you can see many of these websites that generate these fake images or fake faces that are not real people. Okay. Now, again, it's a cool visual thing to do faces, but the underlying technology, really what it's doing is it's learning these sort of very high dimensional correlations, high dimensional structures with very little human expertise. Okay. Now, the name GAN has nothing to do with adversarial ML, right? It is not trying to attack machine learning. In fact, what adversarial network here means is the way in which the model is trained has both a generator and a discriminator, And those things are adversarially training each other. It's kind of like an iterative process where a generator and and the discriminator are trying to defeat each other. And that adversarial training process seems to be very critical to get these high fidelity models. Okay. Now, of course, I don't care about faces. You don't care about faces. We care about realistic data sets that happen in cyber physical systems, networks, and other kinds of like use cases. So the sort of the motivating question for us was, this looks extremely promising in these image data sets and other kinds of applications. Is it possible for us to extend this promise of GANs and put them to a good use, right? So far, most of the use cases for GANs have been sort of negative or just toy, right? Either deep fake or generate some funky celebrity images, which I don't, okay, to be honest, it has no practical utility. But can we use it to generate synthetic data sets that enable the kind of vision that we have in NetShare with good fidelity, scalability, and privacy trade-offs? And that's really the motivating question of our work, and that's how we got to that. Okay? And this has been sort of a body of work that we've been working on since for the last several years, and it's a number of like open source artifacts that people are building on. Now, it would have been great if off-the-shelf machine learning just worked, and then there is no research to be done. But the reality is, anytime you take machine learning and any of these sort of approaches and try to apply them in a new domain or a new setting, you need domain-specific insights to actually get them to work, right? You actually need to be careful in how you apply this machine learning in a practice. And that's really where our technical contributions lie, in identifying these key problems of directly applying existing machine learning approaches or GANs and extending them to get them to work in practice. Okay, so let's start by thinking about a very seemingly natural strawman solution that if you just read about GANs and you say, okay, look, I know I've done some GANs, I've seen some TensorFlow tutorials, I've seen some PyTorch tutorials. How would I do this model? How do I actually use this problem? Okay. Now, and in fact, there's a bunch of like competing approaches that do exactly this. Okay. So what you would do is take your trace, in this case, say a packet or a flow trace, and you might say, okay, let me think of it as a table or a comma separated file, right? So a table or a CSV is a bunch of rows with a bunch of columns, the columns being features and the rows being, say, individual sessions or individual packets and so on. So you could take that and say, hey, okay, fine. I have these approaches called tabular GANs, which again, not quite images, but work for this sort of CSV table data sets, and say, why not take each individual table or CSV of a trace, run it through a tabular GAN, and then just produce the output of synthetic data, and then maybe we'll be done. So this is a seemingly natural solution, and you would hope that this would work, but unfortunately, this sort of natural solution does not work in terms of the fidelity, scalability, and privacy trade-offs that we care about. Okay, so let me walk you through what are those challenges and how we address them. Now, the first challenge is that for a lot of networking applications and systems applications, we actually care about not just individual rows of packets, but how sort of there is like cross-packet correlations or like flow correlations. So for example, very simple things like the flow size, how many packets belong to a particular flow, right? So a flow might be like a TCP session or a video stream. The size of the flow actually matters for a number of network applications. But if you naively treat this like a table with independent rows, that completely kills this kind of flow level properties of interest to us in the community. Okay? So here are two results from different data sets from both a net flow and a packet capture based data set. And we are looking at the distribution of the flow sizes. So this is a CDF. And what we want is the CDF to be as close to the real as possible. But it turns out we look at a bunch of these off-the-shelf solutions using these tabular and other kinds of approaches. They completely kill this kind of property of flow size. And the real reason is they're actually viewing each row as an independent entity. So if there is like a, say, the same value appears in multiple rows of the IP5 tuple, it actually does not capture that very subtle relationship. So again, the strawman solution of viewing individual entities as a tabular GAN turns out to be the wrong abstraction for our community, for our domain. Instead, what we really want to do And we came up with this idea of really viewing the trace not as a table, but really as a time series. Now imagine I had a bunch of these traces. What you really want to think about is a flow, like say me talking to you or me talking to Netflix or you're watching a video somewhere. So that is a flow. And then you look at the events within that flow. Okay, what are the packets? What are their sizes? What is their inter-arrival time? And then formulate it as a time series generation problem rather than as a table generation problem. So that is, I have a time series with metadata and measurements, and that's what I really want to generate. And by doing that, we can better capture these kind of like flow correlation properties. Okay? So let me do a short detour here in time series GANs and how we solve the time series GAN problem. So this is actually based on our prior work called Doppelganger from IMC 2020.
Hi.
This, yeah, please. Yeah, the question.
Can I ask a question?
Yes, please. Yeah.
So at what granularity are you trying to model in your previous slide? The reason is that I'm asking the question is with NetFlow or something, there are limitations in terms of sampling and the duration at which packets can be captured, in the sense of 5-minute windows or 10-minute windows, etc. But if you're really talking in terms of buffer occupancy sort of questions, then we need much more granular data, right? So how do you take that level of, let's say, aggregation and sort of fill that window, if you will?
Yeah, that's a great question, right? So we are not trying to solve that problem. So what we are doing is we are doing data in, data out. So you may have like some flow traces that are sampled, some flow traces that are unsampled, some packet traces that are like full packet capture, right? So we will preserve the properties of the collection process. So if you were sampling at 1 in 1,000, our generated data will also sort of mirror or mimic that sampling features. So for example, you mentioned buffer occupancy. For that one, you probably do not want to use a sample data set to run that because you will get like some bad results. You may want to have like a full packet capture and actually start from there to study that kind of property. So what we do is we mirror the input data set. And again, it's up to you, to the domain expert, to figure out what input data set should be driving your downstream task.
Thank you.
Yeah, so again, so basically it's like data in, data out, right? So we will mirror the properties of the input data. And again, it's to your discretion and your expertise to figure out what's the right data set to collect, what right data set to use, right? Again, that is not something we can answer, but I think one other thing we can do, and this is like future work, is there are these ideas for what's called data imputation, which is I can fill in the gaps like what you're saying. That's a open-ended problem that we have not quite solved yet. So there could be ways of like upscaling, like in the image world, there is people doing like image super resolution, like from a low res image, I can go to a high res image, and GANs are being used there as well. That's like a very interesting direction of future work that we have not quite tackled yet. But yeah, great question. All right, so let me sort of do a short detour into how we do the time series GAN, because that's also independently of interest. Like for example, a bunch of you might be working in cyber physical systems, collecting sensor data sets and sensor time series, which may not be packaged directly, but have the similar kind of property, right? So more generally, we are collecting, we are trying to generate what I would call like a session journey, right? A user or a device where there is some metadata of attributes of the collection agent or a user, and some measurements over time of like what, let's say whatever temperature or humidity or actions that particular person did. And this is a very general abstraction that occurs across multiple domains, whether you be finance, whether you're thinking of e-commerce, think of networking, think of sensors, think of IoT, security. It appears in every single domain. This notion of a metadata followed by a measurement time series. So it turns out, again, off-the-shelf GANs are actually not great for time series generation because they're very bad at capturing these temporal effects. They don't quite capture the correlation between metadata and the measurements. And there is also a problem of mode collapse where if there are different kinds of lengths or different kinds of like high dynamic range of values, it sort of generates the same value for everybody, right? So it doesn't capture the intrinsic diversity of your original data set and so on. So this was a sort of a problem that we tackled on how to do high fidelity time series or session journey generation. So this was a paper from IMC, the Internet Measurement Conference in 2020, where we came up with this architecture and solution called Doppelganger. And that's in fact the building block that we are using as our time series GAN for NetShare. And the design of Doppelganger came up with a few, what I would say, pretty fundamental architectural innovations in applying neural nets and GANs to this problem. So one idea was to decouple metadata from the measurement, right? The metadata, like an IP header or the sensor operating system, the sensor OS, is different from conceptually the measurement, like a temperature or a humidity or a packet event. So by decoupling the generation, we can say, I will use a multi-layer perceptron for metadata and an RNN for the time series. So that actually decoupling captures the structure better. There is this idea of like capturing these long-term temporal correlations. So we came up with this innovation of what's a batched RNN. Now, RNNs or recurrent neural networks are great for modeling temporal patterns, but they're actually not great if you have like long patterns like diurnal patterns or weekly patterns and so on. So we actually used a batched RNN generation. And then I added some ideas for auxiliary discriminator to combine both the metadata and the measurement generation, as well as this very simple trick called auto normalization to capture the dynamic range of values within a given session, right? So I think these techniques are actually very critical to get a time series session journey generation to be high fidelity. So this is a paper at IMC 2020, and it turns out that this is independently being useful and for a multiple domains, right? There are a number of like fintech startups that have been using this to generate sequential time series data. And in fact, there is a startup called Gretel that's been implementing and sort of popularizing this model of Doppelganger in their internal workflows and for other people using time series GANs as well. So again, this might be independently of interest for people with cyber physical systems or other kinds of data sets which are not quite networked, but this is a building block that we use inside NetShare. Okay, all right. So that was the idea one, is to reformulate this problem as a time series GAN rather than as a tabular GAN problem. Now, a second issue we find is that, and this is a common issue that people find when applying machine learning in practice, is you need to be careful about how you encode your input data into the machine learning model. So in particular, we have things like IP headers, we have things like IP ports, and how you model it and how do you encode those values can affect the fidelity of your learning process. So here's an example, let's look at the right-hand side, where we're looking at a couple of like a few off-the-shelf solutions for GANs and how they model or mirror the top 5 destination ports in the data set, right? This is something we care about, right? What are the most frequent applications that we see? 453 is DNS, 80 is like HTTP. And what you'll see is like, if you just naively use a GAN, it actually kills the correlation. It doesn't quite capture that 53 and 80 are the top ranked ports and so on. Okay, so we have to be careful about how you encode the domain of values before you give it to a machine learning model. And that has interesting implications for fidelity, privacy, and scalability. So I won't go into the details here, but sort of the bottom line here is that you need some domain expertise to carefully encode these different headers and different fields in your data set. So we have come up with an encoding for IP and ports that works well in practice. Aniket, you have your hand up.
Hello. Yeah, am I audible?
Yeah, yes, I can hear you.
So I had a doubt, like in the GANs. So in GANs, so what is it using it at any kind of metric while making the generator and discriminator learn against each other, or like once so that we know how close the data that we have generated, or how fidel the generator is?
Yeah, that's actually a great question. So that's in fact an active area of research itself, right? What are the right kind of distance metrics and what are the right kind of like discriminator and generator architectures? So what we do, and this is actually be a fairly canonical architecture. So we use something called the Wasserstein distance. That's turned out to be a fairly robust distance metric that many GANs are using. And in fact, that's what we use in the design of Doppelganger. So
basically the distance between two distributions. how close my distribution.
Correct. Yeah, exactly. Yeah, so it uses the Wasserstein distance internally. Now, one thing we can do is you can specify other kinds of these fidelity properties I mentioned, and that can be used in the hyperparameter tuning. But the GAN internally just uses like some sort of baseline differentiable distance metric like Wasserstein distance and so on.
Oh, okay, so yeah, actually that was my doubt. Like the RNNs capture the tuning of the RNNs weights capture how fidelity or which type of fidelity you want from the data. And
correct, exactly. But that's part of the yeah. So there is some intrinsic distance metric that the GAN is using, but then in the hyperparameter tuning for the GAN, you might be able to plug in sort of domain-specific fidelity metrics of interest, right? You say, oh, I really care about IP distribution. Okay, you might put a bigger weight on it and nudge the hyperparameters towards that particular thing, but that is not intrinsic to the GAN distance function.
Okay, thank you.
Yeah, great question. Yeah, so again, this is also an active area of research on what is the right distance function that GAN should be using and so on. Wasserstein distance seems to be a popular thing that people are using. Okay. Now, another question, again, this is sort of a general problem, is like all these machine learning things take forever, right? Again, we ran it on like many CPU clusters because we couldn't find a big GPU cluster. And if you look at the fidelity as measured by, say, a Jensen and divergence versus the training time, even for like a small trace of 1 million packets, it takes on the order of like several sort of tens to hundreds of hours with a standard in terms of CPU hours, right? So there is this sort of scalability, fidelity trade-off when you're training these more complex machine learning models. And of course, we want this to be as cheap and as sort of fast as possible. So here we came up with a sort of a practical insight that we can do a couple of systems optimization. So one is, instead of trying to naively learn a model for every single trace or every single epoch in your data set, I think somebody mentioned like every 5 minutes you're collecting an Xflow trace. Instead of learning an independent model for every 5 minutes, what you might be able to do is we learn a model for the first chunk or the first few minutes, and then we can chunk this trace, and then we can use like an incremental or a fine-tuning approach where we use the starting model from the first minute to train the subsequent 5 minutes or subsequent minutes and so on. And this actually gives a much significant speed up. As long as there's not like significant model drift, we do get a pretty significant speed up. And the other nice thing is we can also run those subsequent chunks in parallel. So I've collected a 1 day of data. I can split it into evenly sized temporal chunks and then run those different things in parallel while periodically retraining this sort of baseline model. Okay, so again, this is now turning out to be a fairly standard practice in the machine learning literature on how do you operationalize machine learning. This is actually a system level optimization that we can do as well in training NetShare. Now, the last part comes back to this challenge of privacy. Now, again, I think how do you incentivize people is you have to convince them that we provide some kind of like intrinsic privacy properties so that people are willing to share these data sets both internally and externally. Now, one concern, and I think this is actually a valid concern today, is that people sort of naively apply differential privacy to anything that they see. But it turns out if you naively apply differential privacy to something like a GAN, it's actually pretty bad. It destroys the fidelity even with a weak privacy property. So for example, the graph here shows the trade-off between the fidelity as measured by sort of an earth mover distance metric and the fidelity and the privacy as measured by the differential privacy epsilon parameters. These are actually fairly weak epsilon values. And what you see is like even with some very weak epsilon, naively using differential privacy completely kills the fidelity that we want. Okay, and actually this is not good. So this has actually been a problem in the GAN literature. So what we observed was this opportunity to do again something a little bit more practical. So what we do is instead of naively training a differentially private SGD or a stochastic gradient distance model, what we do is we take a small amount of public data. So imagine there is some industry consortium or any kind of public data for a data center or any kind of other setting. We take a small amount of public data, pre-train with the public data, and then apply the differentially private learning on your individual private data set. And that turns out to be much better in practice, in the terms of the differential privacy versus fidelity trade-off. Again, this is turning out also to be a fairly canonical workflow that operational machine learning and operational use of like differential privacy is using these days, is to use a combined public and private data. Now, on top of that, we can also do, I think this goes back to sort of Parimal's original question, we can do a bunch of other canonical things because the architecture is quite flexible. We can do things like remap the IP addresses, hide attributes, hide distributions, many other flexible things where you can specify the privacy properties of interest to you and apply them on top of the trace that we generate. Okay? So we can do a lot of like practical privacy things in addition to these theoretically strong privacy properties like differential privacy. Okay. All right. So just to summarize sort of the key ideas, right? The challenges we saw were in terms of fidelity, in terms of like this, how do you encode the data, how do you get scalability, and how do you get privacy? And we have a few key ideas. One is to reformulate this problem as a time series problem to capture the correlations of interest to us, using these sort of domain insights to improve the data encoding. This combination of like fine tuning plus parallelism by chunking gives us a pretty significant speed up, and then using a small amount of public data improves the privacy versus fidelity trade-off in practice. Okay. So the end-to-end view, right? So imagine you're a data holder. How you would use NetShare is essentially you would do the step of like combining these traces, create a flow-based reformulation of the problem, then you would chunk it, then run the time series GAN with fine tuning for every single epoch, and then you can either share the model or share the data set with your collaborators. Okay? So that's sort of the end-to-end flow for NetShare. Okay, so maybe this is a good segue. Let me try showing you a very quick demo of what the code looks like, so that you can try it yourself, as well as what the dashboard looks like. 1 second, I'll stop sharing my slides and I'll switch to my screen. Okay. Do you see like a Mac Vim window with the code, with code snippets?
Yes.
Okay, great. So this is essentially what you would need to do, how to use NetShare in practice. So we've actually released it as a very usable sort of Python-based implementation. So we use Ray for cluster management. So Ray is an open source, Apache open source project. So what you would need to do essentially is very simple. You would need to create like a config like this, right? Specify where your data is coming from, what data format you have, how many chunks you have, do you want to use differential privacy, and so on. Now, if you're an expert user, you can also change a lot of the machine learning parameters. Like for example, okay, what do you want to pre-process? How do you want to change the hyperparameters of machine learning? Do you actually want to change the batch size? Do you want to change the RNN, the MLP model, how many rounds, and so on? But in practice, we don't expect for most cases that somebody needs to change those sort of low-level hyperparameters in the machine learning model. Like you wouldn't have to change the number of layers, the number of units, and the attributes, and so on. So those are fairly robust configurations. What you would typically need to do is just point to a particular data set, give us a format, and then run it on your own cluster. So we're actually we can support Ray, and you can set up a Ray cluster on like Azure or Amazon or wherever, and be able to use this kind of toolkit. I think there is a link to the open source code at the end. So please do try it out. We're trying to make it usable for people. We want more people to use it because this is a problem that comes over and over again. So I'll give you a link to the code at the end. You can also see, 1 second, let me do one more thing, is once you run the code, we can also generate some kind of like a flexible dashboard like this, where you can visualize the performance of NetShare in this or any other toolkit that you're running on different kinds of distributions, like the source IP, the destination port distribution, the IP protocol distribution, the flow sizes, the flow duration, the number of bytes, and other kinds of properties of interest to you that you can plug in. So these are the kind of fidelity metrics you as a domain person might care about. And you can plug in this and plug in these as basically Spark programs or Python programs to evaluate the real versus the synthetic data set to validate visually that it's actually generating a good model for you. So this is like, it just generates a visualization dashboard for you to test it out as well. So this is the part of the open source package that we have released. My students have done a fantastic job of making it usable. So please do use it and try it out and give us feedback. Let me go back to my slides. Okay. All right, cool. Are the slides back up?
Yeah.
Okay, all right. So how do we evaluate NetShare? So we've taken a number of like public traces. Again, we don't have proprietary traces right now. So in the interest of reproducible research, we've taken a number of public traces from different settings, including data centers, enterprises, and other kinds of like capture the flag events. And we look at different kind of statistical properties of interest, right? How well does NetShare match the source address distribution, destination address distribution, source port distribution, and so on. So these are kind of metrics, as well as other kinds of temporal properties that somebody asked about earlier. So again, I sort of point you to the paper to look at like a bunch. There's like a ton of like statistical properties of interest, including the stuff you saw in the dashboard. So the bottom line here is across a number of traces, across a number of these metrics, NetShare is significantly better, like around like 40 to 50% better than other baselines and off-the-shelf GAN architectures for both flow as well as packet level traces. Yeah, there's a question. Preetham. Yeah.
Yeah. So could you elaborate on the fidelity aspect, because this will be domain specific fidelity, and like, is there a kind of a well-defined parameter, like, okay, you are maintaining the fidelity of interarrival time or the fidelity of the packet size distribution? Do you have a formal kind of notion there?
Yeah, great question. So in this case, so again, the fidelity metrics is generally an open question, right? How do you know that your synthetic data has captured the real data well? So this is where a domain expertise has to come in, right? So imagine you have like some sensor networking data set or some CPS data set. So in this case, we picked a number of metrics that we know are important from the networking community, right? Like 20 years of measurement research, we have looked at all sorts of statistics of interest to us. Interarrival times, address distribution. So that's what we are codifying as the fidelity metrics of interest to us. And then you look at the distribution characteristic, like say in this case, the Jensen-Shannon divergence or earth mover distance or whatever is relevant to you. So that is one way of measuring fidelity. The other way of measuring fidelity, and I'll actually get to that in a second, and this is a nice segue, is you not only care about the statistical properties, but you also care about downstream tasks, right? Maybe you're doing some anomaly detection on top of it. Maybe you're doing some heavy hitter detection on top of it. Maybe you're doing other kinds of like traffic prediction. You also want to check if those downstream tasks are equally high fidelity in addition to sort of baseline statistics, right? So these are more emergent properties of the trace, not just statistical properties. So we actually do evaluate and allow you to plug in different kinds of these downstream tasks. So in this case, for example, we looked at a sketch-based or an approximate randomized algorithm for telemetry, and we show that the NetShare is much better than baseline. And more importantly, what you want to do here is you're often looking at sort of evaluating the synthetic data to evaluate different algorithms, right? You want to say, hey, if I do make a decision based on my synthetic data, does it work well in practice? And that's exactly the question we're answering here. We actually show that NetShare preserves the ranking of these different approaches. So here we have like different kinds of, like say, heavy hitter detection algorithms, and we are showing that using the synthetic data preserves the ranking. So the structure is preserved, even though the absolute values might be different, it's preserving the rankings in that sense. Yes, Parimal.
Sorry. So what I didn't understand is that, so suppose you want to do this heavy hitter detection, right? So you'll write an algorithm, correct?
Yep.
And there'll be real traffic, and then you'll be able to detect the heavy hitters. So what I'm not understanding, how is NetShare helping with this?
No. So here what NetShare is helping you is evaluating what algorithm to use, right? So suppose there are 4 different algorithms for running heavy hitter detection, and then you say, which one should I be running in production, right? So in your test data set, in your offline training or offline, you're basically saying, okay, I have some synthetic data. I do some test-driven development to figure out what algorithm to use. Maybe you say, oh, count sketch is better than count min sketch, or this Unimon is really bad. Okay, actually, Unimon is also our work, right? So you might actually say, you might want to do which algorithm is best on synthetic data, and that's what you want to run in production.
Right? So if my understanding is correct, so what you have to be saying is that, look, so there are certain features of heavy hitters, and if your model is not correct, your algorithm might be focusing on the wrong features, which NetShare is able to bring to the forefront. That is the right thing.
Exactly, right? Or like some particular configuration of your algorithm was not good enough, right? So say, okay, you can basically test and develop your algorithm in offline stage using synthetic data.
But that configuration is a bit tricky business, right? Because when you develop an algorithm, that configuration would have to be changed according to when you are running,
but again,
right?
but I think, but you do, because the data set that we are generating is based on the real data, right? So you're actually tuning based on the real data. The actual performance might be different, right? Say, okay, you get 5% accuracy in the real versus like say 4% accuracy in the synthetic. But you might say, okay, how much memory do I give it? How do I configure it? That you can actually get some rough tweaking with the synthetic data as well, because we are capturing the statistical properties, the workload properties of interest to you.
I see.
But I mean, I agree.
What I was saying, that the statistical properties would change, right? I mean, if like, so you gave me one real traffic from that NetShare is gonna say this, and based on that, you're gonna put some, configuration. But then another real traffic comes, and probably have to use.
Oh yeah, of course. Again, of course. So what we would do is, like, in any given deployment setting, right? You would have to have it. You'll have to use NetShare over like a bunch. You wouldn't just do it on one trace, right? You would take a sequence of traces from your deployment and then see what configuration works robustly across those different traces. You wouldn't just take like one minute trace and say that's an optimal.
So, I mean, so just like speaking, like maybe not related to this work, but I'm saying that in general, what you would like to do is that you would like to have a good algorithm, and this configuration you might want to learn on the fly, right?
Yeah, exactly. Yeah, the configuration you would have to tune it in the real world, right? And you would have to actually watch the performance in the real deployment. But you can get some rough bootstrapping or some rough configuration insights using synthetic data, right? Rather than operating in the blind, you actually have some good starting points for your configuration. You would have to tweak it in the real world, right? You can't just say I use synthetic data and then all everything is good in the real world. You would have to do some real world watching and so on, and tweak it and tune it in the real world. But you can get some good starting points of what algorithm, what configuration to use. So we also use a bunch of other downstream tasks. For example, there is a lot of interest in looking at header-based anomaly detection, right? Is there an attack? Is there a DDoS attack, and so on? So we take an open source code called NetML from other groups that look at like different header properties and anomaly detection. And once again, we observe this property that using the synthetic data preserves the rank correlation of different algorithms, right? So now you have confidence what algorithm you should want to use in the real world by testing and training on synthetic data, that rather than sort of operating in the blind. Similar results hold for like application type prediction, right? So people in ISPs want to do things like, hey, is this video, is this web, so that they can do different classes of service or different kinds of optimizations. And they're using like header-based traffic prediction for flow type based on flows. Once again, we say this thing about NetShare. Using synthetic data from NetShare preserves the rank correlation across these different classifiers, again, giving you confidence on what classifier to run in practice. So back to this original question of fidelity, right? There is no good answer. You have to have domain expertise to plug in different kinds of statistical properties. And we can give you a library of known properties, and we can give you like a framework to express these different things as user-defined functions, as well as writing these downstream tasks for you. But the nice thing is, because the way NetShare is structured, it creates a data set in your original format. You might already have written workflows for this kind of downstream task or statistics of interest to you. You don't have to change anything on your code, right? If you've written Spark code or Python code or C code to ingest a PCAP or any kind of trace format, you can use the same thing with the NetShare generated code. So because it's like, you don't have to change any of your workflows to test it out.
Hi, this is Chandramouli again. Another question, or maybe even a delicate question. One of the things that we were at least puzzled about was, and you may have also, was the Facebook data set where they had the data center characteristics.
Yep.
And actually, I felt it had actually very minimal information and like almost like a movie trailer,
Yeah.
So,
No, that's a great.
okay.
Yeah.
But it didn't tell. Yeah, it gave us some information, but it actually didn't give a lot of information.
Yep.
Will NetShare help in that sort of situation?
Great question. I've actually had a bunch of conversations with my colleagues at Facebook on this exact question, right? That Facebook data set is like highly anonymized, highly sampled, right? And that's the reason is because that was the only thing they could get past their legal team at their time. And in fact, they've even stopped sharing the data set now, right? They've stopped putting out new data sets. So again, this is actually a problem, right? You say, okay, what people are sharing is extremely useless for us to evaluate a data center architecture or anything, but they did a great job. I mean, to their credit, they managed to push it through legal and other kinds of things. But maybe if they have a toolkit like NetShare in the future, maybe it will incentivize people to do better sharing than the coarse-grained sharing they had to do earlier, right? They had to do this heavy anonymization, heavy sampling, because that was the only thing that they could do. That was the only hammer, that's a coarse-grained hammer that they had at the time, right? My hope, and again, this is the vision, is that with a framework like NetShare or other and people building on it, it can now create incentives for those kinds of productions and operators to actually share more data set with academia that they could previously not. And we are actively talking to them and trying to see if we can actually get them to use NetShare and put out new data sets. Again, that's an open question that we haven't quite answered yet. Yeah. So we are giving them the tools, right? They don't have the tool. Because they don't have the tool, they're doing something crappy, which is not useful for you. But hopefully with a better tool, we can actually change the status quo. And that's really the vision we are going after.
Okay, thank you.
All right. No, great questions. Yeah. So yeah, and you're right. So this is exactly the kind of pain points we are trying to solve, right? But again, we are not far from done. We actually think that NetShare is only like a first step towards this longer vision of incentivizing data sharing and collaborative workflows. A bunch of limitations that we have to acknowledge, right? We only do header and flow traces. We don't do stateful protocols like TCP, session-oriented protocols, or payloads, or application-level features. Those are all things that we want to do. There are many more downstream tasks and fidelity metrics of interest that we have time and resources to try. Do you want to do quality of experience inference? Do you want to do device fingerprinting? Do you want to do security attack detection? Those are all things to worry about. How do we improve the scalability further? Are there other kinds of downstream tasks for which you want better scalability? Now, and sort of even more important open question for us is talking to practitioners and saying, hey, what privacy property do you actually care about? What would incentivize you and your legal team to allow this data sharing? And maybe it's not differential privacy, right? Maybe that's not what you care about. Maybe what the people care about is not revealing how much volume they have, where their servers are located, what their topology is. Again, all these other privacy properties for our domain, for CPS, is actually not very well studied. So that itself might be a very rich direction of research to think about domain-specific privacy properties to incentivize data sharing, rather than just throw this blunt hammer that we have called differential privacy. It's a great idea. It's a great theoretical toolkit, but it's just like one idea, right? It's one formulation of privacy. Maybe there are other privacy properties we should be exploring for different domains. All right. That's basically it, what I had. So again, as I said, this is actually almost like a 2-decade-long pain point of not being able to get data for my research. And this is like academia and industry are struggling today as they are moving towards more data-driven workflows. Those workflows are being stymied by data access, retention policies, and data silos. Now, synthetic data is a new opportunity, and our work is just a first step looking at the feasibility and promise of GANs. And again, our early results show it's robust across data sets, domains, and downstream tasks. But really, there's a ton of work to do, right? Again, I believe this is going to be the future with more privacy and compliance regulations. This is part of a broader project and many other contributors. Do try it out, right? We do have an open source version. We want more people to join us, contribute, test it out, add more features, give us feature requests. And again, this is not going to be a one person or a one group project. This has got to be a bigger community effort. So if you're interested in collaborating, joining forces, please do let us know, and we'd be super happy to collaborate and help you get it set up as well. And that's all I had. Thank you for your questions. I'm happy to take more questions, but I don't know what your timing constraints are. Thanks again for setting this up. This has been a lot of fun, and I'll take more questions.
Thank you, Professor Sekar, for an informative talk. Any further questions?
I see one hand up.
Preetham again. Yeah, so can you elaborate on the limitations part? You said you are doing header traces and net flow traces, but you can't do the session oriented or the statefulness. What is the roadblock for getting the statefulness captured?
So I think stateful protocols typically have like some sort of a request response causal feature, right? Like I send you a SYN, then you send a SYN-ACK, right? Very basic TCP stuff, right? Now, how do I model that in a GAN? That causal relationship between events is not something a GAN can currently capture, right? And we have to figure out how to encode even very basic things like that, right? The response to a request depends on the request, right? That is not something we can currently do. So we actually look at like packet arrivals, but not the values of the packets or the fields inside the packets and so on that might have dependence between the previous history. So those are things that stateful session-oriented protocols will need. And maybe there are ways to do it. It's just that we haven't done it yet. If you have cool ideas, please let us know. As I said, these are open questions, right? I mean, these are all like PhD research projects or ideas for you to write papers on. Yeah.
Right. So I'm again like thinking just aloud. So if you're capturing all the headers, then that information is still there. Like I don't know whether you are capturing this temporal relationships, but the header information is still with you, right? If you're talking about the raw packet capture.
Yeah. So right now we don't actually capture those header fields, right? We're actually not capturing TCP flags because those are deeper into the header, right? We are only capturing the IP phi tuple like flow and packet headers. We're actually not capturing like deep flags and so on. So yeah, maybe this is trivial. I don't know. I just like have to be honest where our limitations like. So if you find that it can do it automatically, even great, even better. My suspicion is it's not that trivial, but yeah, that's my intuition. It's not trivial.
So as of now, the fidelity also is defined on the phi tuple, is it? Or
mostly on the phi tuple and other kinds of fields in the packet header, like a subset of the fields, right? It's not looking at all flags and all kinds of things. So I mean, even basic things like, for example, there is like say checksums and TTL, right? Those are not something we can do as a GAN to generate. Very basic stuff, right? Okay, I didn't talk about that, but you do not want a GAN to generate a checksum for your packet header because that's a very complex function that's impossible for machine learning. I mean, not impossible, very hard for machine learning algorithms to learn. But you may want to learn things like checksum and other fields outside GAN. That is actually something that we do in practice as well, right? So those kinds of relationships or interdependencies are hard to express directly as a machine learning problem, which you have to be careful on how you encode those requirements.
Okay, so I'm very naive at these ML domains. So I'm just trying to understand, if you were to add those other header fields, then what is the limitation? Is it the model size or the training effort? Or?
No, it's the model expressive enough to capture those things, right? It's not naively adding just more header fields. We can add more header fields, right? But if there are stateful dependencies or causal dependencies, it's not obvious that the model can currently directly capture them. Right.
Can I? I mean, can I make a comment if I may?
Yeah,
I mean,
please. Yeah.
I shouldn't be answering on your behalf or something.
No, sure, please. Yeah. Okay.
No, I think to Preetham's thing, it depends upon how you're going to use the trace. If you're going to use the trace to pump a router, then you need all the CRC header, everything. Otherwise, the packet will not be switched. But I think they are only looking at these sort of macro level features of the trace and then compare that with what is presented by the model. Not actually, what shall I say, put the router in a load or something. In which case, you need all the CRCs and everything, etc. Otherwise, the packet will not be switched.
Correct.
Otherwise, if you don't do that,
that's one example. I think he was asking more about the stateful part, but I was just saying, yeah, in practice, you have to be careful about doing a bunch of things, right? So CRC was a very simple example. I think checksums, but I think more generally, if you want to do stateful and say, okay, look, the client and server both have to respond correctly, right? That protocol semantics and so on is actually pretty hard to capture directly using a GAN. But now, on the plus side, there are new emerging models like diffusion models and other kinds of things that are based on language models that might be better for capturing those stateful protocols. That's a very interesting direction of future work. So I'm not saying it's impossible. I'm just saying we don't do it yet. So, but if you have clever ideas of doing it, please, all power to you.
Yeah, so this is quite cool and interesting. Just wondering on how to like extend the usability beyond what you illustrated. So, like to Molly's point about replay. So it's not just about replay on routers, but even for say inferences. Like how do you characterize the workloads given the traces, synthetic work traces, or how do you detect heavy hitters, or how do you detect microbursts? There, these beyond the phi tuple, the additional information can be very useful. In fact, again, going back to the utility of the Facebook type traces, I think that would be the thing, right? It's too much
exactly.
anonymized.
No, as I said, this is the first step, right? I mean, with the Facebook data, you can't do microbursts, right? Because it's like so heavily sampled, it's not packet level stuff and so on. Yeah, absolutely. I mean, as I said, this was a long time coming. This is itself like a significant challenge, but there's more stuff to do. There's way more work to do, and then we have like the resources to do. So that's why this has to be a broader community effort. So if you have like cycles and are excited to try out this new use case of like microbursts and how to get microbursts to work, we would be super happy to help you get it set up and collaborate and so on.
So I missed the part about the usability aspect. So you have released it as a library. So is it like a model with the weights that we can apply to our, say, if we have a existing trace, internal trace, can we take your library as a set of weights, parameters for the model?
I think you'll have to train it a little bit. You'll have to relearn it. So you'll have to run the learning on your own. I wouldn't just take the model that we have. So we're not releasing the models, we're releasing the code. So you would have to run the learning and run the learning process in your cluster on your trace, and we can help you set it up. Yeah, I wouldn't, it's not like a BERT or one of these foundation models where you say, okay, everybody can just take this model, right? I think you'll have to take the code and relearn the model for your own setting. Yeah, this is, do not think of this as like a foundation model where this is the universal model. We have a universal workflow that needs to be applied to your setting.
Okay, and how computationally demanding is this kind of library?
I think that there are benchmarks in the paper. I think for like a 1 million trace, like a 1 million packet trace, it takes on the order of like a few tens of hours. And again, we are working on improving the scalability, but that's kind of where it is right now. Just on a CPU cluster with GPUs, you get an order of magnitude speed up, but we don't have the money for a large GPU cluster.
Thanks.
Yeah.
If no more questions, we can end the session here today. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on our future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the web page. Thank you and have a great evening.